This video is about predicting products for single replacement or displacement reactions. Sometimes it's called either one, replacement or displacement, using the activity series. Okay, first, before we actually begin talking about how to predict products, we need to look at what a diatomic molecule is, because this will be real important in writing reactions. A diatomic molecule is composed of only two atoms of either the same or of different chemical elements. We're concerned only with the diatomic molecules that have two of the same elements. There's 7 of them, diatomic molecules you'll need to know. Starting in the left upper hand corner of the periodic table, there's hydrogen, so H2. Go straight across to the first gas towards the top is nitrogen, so N2. And then oxygen gas, O2. Straight across, fluorine gas, F2. Straight down the halogens, chlorine gas, Cl2. Then there's bromine, which is actually a liquid, but it's still diatomic. And then there's iodine, which is actually a solid at room temperature, but is also diatomic. So anytime in a chemical reaction you have these elements, these substances produced by themselves, not in a compound, but by themselves, it will have to be diatomic. So it's when you have just hydrogen, hydrogen is going to be H2. Okay, now for a single replacement, there's 2 types, and the first type we're going to deal with has a metal ion. So this A here is going to represent our metal ion. And what the metal ion does is replaces the other ion that's in solution. So Bc here is in solution. And remember, you always write the metal first. So B is our metal that is in the solution. So A, if it's stronger than B, will come along and push B out, and B will end up by itself over in the product side. A then takes B's spot. Remember to write A first, because you always put the metal before you put the nonmetal. And in this case, C's representing the nonmetal. And of course, then we would have to balance our equation. So here's our first example. We're going to add magnesium metal to a solution of silver nitrate, actually, not chlorate. So let me cross that out. It's going to be nitrate, because that's how I already have it written. And it causes magnesium to not dissolve but to react, and the silver to precipitate out, or in other words, become a solid. So here's our equation, AgNO3, silver nitrate, and a magnesium metal. Now, magnesium is going to push out silver if and only if magnesium is stronger than silver. So how do we know? On the back of your tables, you have what? A reactivity series. This right here is our reactivity series with the most reactive at the top and the least reactive at the bottom. So we are going to look for magnesium. Right here is magnesium, and down here is silver. So magnesium, which is the one that needs to replace the silver, is stronger because it's higher on this chart. So now you can go ahead and know that magnesium is going to push out silver. Silver will end up by itself, and it'll be a solid. And magnesium will end up joining nitrate. Now, anytime we write a compound, we got to always do charges. So we actually need to go, okay, Mg is +2, nitrate is -1, and switch it. So we get MgNO3 2. Now, to rewrite the equation then, we have silver nitrate, which is in the aqueous form, plus magnesium solid produces silver solid plus magnesium nitrate, which I'm running out of room there, but it would be a solid. So, I mean aqueous. So you could put Ag after the magnesium nitrate. Now the last thing before we do anything else we need to do is to balance. Now I have 2 nitrates on this side, and this side I only have 1 nitrate, so I actually need to sneak in a 2 in front of the silver nitrate, which also gives me 2 silvers. So over here I need a 2 also in front of the silver. Okay, let's try another example. Potassium solid is placed into a solution of silver fluoride. In this case, potassium needs to be stronger than sodium. So once again, we're going to check our activity series. Okay, on our activity series, here's potassium and here's sodium. So even though potassium is not a lot stronger than sodium, it is stronger. So potassium will still replace sodium. So in this case, K is going to push out Na. The metal pushes out the metal. Na ends up by itself and it's a solid. K ends up with F, aqueous. And potassium is a +1 and fluorine is a -1, so it ends up being just Kf. Now if we balance it out, we see we have one potassium on each side, one sodium on each side, one fluorine on each side, so it just happens to already be balanced. Let's try one more example. Okay, and this time silver would have to be stronger than lithium in order to get the reaction to occur. So we're going to go check our activity series again. On our activity series, we see that lithium is at the top and silver is towards the bottom. But silver is the one that needs to replace lithium, and silver is not stronger than lithium. So now what do we do? In this case, you can't write a reaction because silver is not stronger than lithium, so you simply write no reaction. You would not see anything happen if you put the silver metal into the lithium fluoride because silver is not strong enough. Now, let's look at the second type of single replacement. The second type of single replacement is instead of having a metal, we have a nonmetal here, which would be one of our diatomic substances that we talked about earlier. And in this case, the nonmetal is going to replace the nonmetal. So Y is going to push out X. X will end up by itself and usually will always be diatomic. And Y takes X spot. We're going to put Y in the second spot because Y is the nonmetal and the metal always comes first. So A, the metal stays in front, and Y, the nonmetal, goes in the back. And then, of course, we would have to balance this. So for an example, we could add chlorine gas to a solution of sodium bromide. So we would have Cl2 gas going into sodium bromide, Na+1, Br -1, so that's okay. And this would be our reaction. Now, just like before, chlorine has to be stronger than bromine or the reaction will not occur. Well, how do we know if chlorine is stronger than bromine? Nonmetals, we're not going to use the reactivity chart. For the nonmetals, you simply use the periodic table. As you go up the nonmetals, the group of the halogens, it becomes more reactive. So fluorine is the most reactive element of the halogens. And we're usually only going to use the halogens in our reaction. So since chlorine is further up than bromine, chlorine will push out bromine. So Cl2 will push out Br. Br, when it's by itself, remember diatomic, and it's actually a liquid. And then sodium stays first, chlorine goes second. Check charges. Sodium in group 1 +1, chlorine group 17 -1. So we don't need any subscripts. This becomes aqueous. Now we do need to balance. Over on the reactant side, I have 2 chlorines, where over here I only have 1, so I had to put a 2 in front of the sodium chloride. That gives me 2 sodiums, so I need to go over here and make 2 sodiums. That now gives me 2 bromines, which I already have. So now we're balanced and the reaction is complete. Let's do one more example. This time fluorine needs to push out iodine, so we have to go over here and see if fluorine is more reactive than iodine, looking at the periodic table. And yes, fluorine is the most reactive element in the halogens. So fluorine will push out iodine. Iodine will stay by itself, I2, which is actually a solid. And then fluorine takes iodine's spot. Remember to put fluorine second. We had to check charges. Calcium this time is in group 2, so it's a +2, or fluorine as a halogen is -1. So we're going to switch it, and it's going to become CaF2. So now we need to rewrite all this. CaI2 aqueous plus F2 goes to I2 solid plus CaF2 aqueous. Okay, now we need to look to balance it. There's one calcium on each side, two iodines and two iodines, two fluorines on each side, so it's already balanced. That will conclude our reactions for single displacement or single replacement. Remember, there's two types. There's where you have a metal that's the single substance and it's going to push out the metal as long as it's more reactive. And then you have the case where you have a diatomic nonmetal, which will push out the nonmetal as long as it is more reactive.